Problem 1. Two ropes are attached to a 40 kilogram object. The first rope applies a force of 25 newtons and the second 40 newtons. So 25 newtons, and we'll put a little object down here, and 40 newtons. If the two ropes are perpendicular to each other, what is the resultant acceleration of the object? Acceleration equals the sum of the forces divided by the mass, Newton's second law, and our mass is, so this is going to be, say, 0,25 plus 40,0 divided by our mass of 40 kilograms. So we've essentially got this vector of 40, 25 over 40, and of course the magnitude of that vector is square root of 40 squared plus 25 squared. Which comes out to be 47.16. We'll divide that by 40 to get 1.18. And to two significant digits, that is 1.2 meters per second squared. Number 2 asks, we have an acceleration of a 20 kilogram object at 6 meters per second squared on the moon. Acceleration equals the sum of forces divided by the mass. And this is actually a very simple question, the first part. What net force would be required to lift it 6 meters per second? 6 meters per second squared equals the net force divided by the mass, and we got a 20 kilogram object, so it's just 20 kilograms times 6 meters per second squared, or 120. So the first part is 120 newtons. But then I ask, what is the necessary applied force to lift the mass straight up? For that question, we need to break down the sum of the forces into force applied plus the force of gravity on the moon, which is going to be mg over 6, the same as the force of gravity on the Earth divided by 6, and we'll divide that by m. So here, this is Newton's second law, and I'm going to solve that for the force applied, which is going to be mass times acceleration minus mg over 6. So let's pull that a out of there, or pull that m out of there. We'll have a minus g over 6 equals 20 kilograms times acceleration. We've wanted to accelerate at 6 meters per second squared minus 9.8 divided by 6. And this comes out to be 87.3 newtons. And I didn't put that answer over there, so I'll just put a box around that. It's not in the multiple choice list. For number 3, we've got a 70 kilogram man jumping 1 meter straight down onto a concrete walkway. His downward motion stops in 0.02 seconds, and if he forgets to bend his knees, what force is transmitted to his leg bones? The equation for this from chapter 4 is basically acceleration equals the sum of forces divided by the mass, and we will need to find the acceleration. We also have a formula from chapter 6 says force equals delta P over delta T, change in momentum over change in time. Okay, problem number 3. A 70-kilogram man jumps 1 meter down on a concrete walkway. His downward motion stops in delta T equals 0.02 seconds. If he forgets to bend his knees, what force is transmitted to his leg bones? Gotta draw that guy up there. Okay, here is a couple of interesting things. We're going to need to figure out, first of all, how fast he's going when he hits the pavement. And we can do that using either methods from Chapter 3 or Chapter 5. Chapter 3 had the kinematics equation, v final squared minus v initial squared equals 2a delta x. You can say the acceleration is g, the delta x is the height, and the initial velocity was 0. So you solve that and you get square root of 2gh. You can also get it by from the methods of Chapter 5 by noting that the final kinetic energy is equal to the initial gravitational potential energy. So that gives you 1/2 mv squared equals mgh, and also you get v equals square root of 2gh. So let's put that down there. Either one of those methods works fine, so we'll just write the final equation, which is square root of 2 times 9.8 times 1, which comes out to be 4.43 meters per second. Now, for the next part, we need the force that is on his knees. And for this, we can use methods from either Chapter 4 or Chapter 6. In Chapter 4, we learned about Newton's second law. Acceleration equals the sum of the forces divided by the mass. And here we have mass times acceleration equals the net force. And acceleration is delta v over delta t, so we can find force m delta v over delta t. In Chapter 6, we learned that the net force is equal to the change in momentum over time, which is also m delta v over delta t. So the net force on his legs, or on his knees, is going to be m delta v over delta t, which is his 70 kilograms, times his change in velocity, which is 4.43, divided by that change in time, which is 0.02 seconds, which comes out to be about 15,500 newtons. Kilogram meters per second squared. Number 4, I think, can also be done with 2 different methods. One is through finding the kinetic energy and the work, and the other one is through force, acceleration, and delta x. If we did this one, we would have the kinetic energy at the beginning, 1/2 mv squared, would equal to the work done by the friction, which would be the force times distance, which is usually mu times m times g, mu m times the normal force. Okay, or mu times the normal force. Anyway, we don't need to use the normal force this time because we know it's 10,000 newtons. We also know 1/2 is, and then we'll take 2,000 kilograms, and the velocity squared, 30. So that would give us the answer. The other way would be through finding out the acceleration, would be 10,000 newtons divided by the mass of the car, 2,000 kilograms. And then finding delta x through v final squared equals 2a delta x. So delta x equals v final squared divided by 2a. So the acceleration is 5 meters per second squared, and the distance traveled is 30 squared divided by 2 times 5. And you can see that both forms come out to be 90 meters. So the answer is B. Number 5, an elevator weighing 20,000 newtons, let's see, mg equals 20,000 newtons, is supported by a steel cable. What is the tension in the cable when the elevator is being accelerated? Acceleration is 3 meters per second squared. The answer we will have, this is a Newton's second law question. So our sum of forces will be the tension acting upward minus mass times gravity acting downward divided by the mass. We will have to calculate the mass, I guess. From this, m equals 20,000 over g, which is 9.8, which comes out to be 2,040 kilograms. 2,041, I guess. All right. Mass times acceleration plus mg equals tension, and that can be converted into a plus g equals tension. So we'll have 2,041 times our acceleration of 3 plus 9.8 will be our tension. And it came out to be 26,124 newtons, which is answer D. Number 6, a horizontal force of 750 newtons is needed to overcome the force of static friction between a level floor and a 250 kilogram crate. So this would mean the force of friction, static, is mu sub s mg. This is the normal force right here. And so equals 750 newtons, and that is max. 750 newton. We could find out what mu sub s was if we wanted to. It's not asking for that though. It's asking for the force of acceleration after. This would be max. Okay, so after that goes on, we will have the force of kinetic friction equals mu sub k mg. So that is actually, we actually know it. They tell us mu sub k is 0.12 times our mass, 250 kilograms, times gravity is 9.8. And okay, what is the acceleration? Acceleration equals the sum of forces divided by the mass. We will have 750 newtons, 750 newtons going that way, and the force of kinetic friction going that way. So it'll be 750 minus, let's go ahead and calculate that. This is going to be 294 newtons right here. The force of kinetic friction minus 294 divided by mass of 250. And that comes out to be 1.824, which rounds to 1.8 meters per second squared. Let's go ahead and calculate the mu sub s while we're here. We know that mu sub s times mg is 750 newtons. So mu sub s equals force of static friction max divided by mg. Yeah. And so that would be 750 newtons divided by 250 kilograms times 9.8 newtons per kilogram. Which came out to be 0.306. I wasn't asked, but I think it's a good question.